Well, hello and welcome to our third Thursday webinar. I am Tom Sandry, and today we're going to be looking at an introduction to potential and current transformers. Now, the topics that we are going to be covering in today's webinar include the current transformer basics, the objective of the current transformer, functions of the CT. We'll talk about burden on a CT, typical saturation curves, why is saturation important, principles of differential protection, and testing of the CT. From there, we'll move on to potential transformers. And once again, we'll cover the objective of the PT, the function of the PT, connections of a potential transformer, types of PTs based on their function, errors in PTs. Also, we'll look at impact of burden on the PT, applications for the potential transformers, and then a review of testing of the potential transformer. All right, so let's get started. Now, current transformers are commonly used devices found in metering and protection relay applications for the electrical power industry. The purpose of these devices is to scale large primary currents to a smaller, easier to measure secondary current. The device also isolates the measuring and recording instruments. Now, current transformers, or CTs, together with voltage transformers or potential transformers, VTs or PTs, are all known as instrument transformers. Now, like any other transformer, a CT has a primary winding, a magnetic core, and a secondary winding. Alternating current flowing in the primary winding produces a magnetic field in the core, which in turn induces a current in the secondary circuit. Now, the objective of the CT design is to ensure that the primary and secondary circuits are efficiently coupled so that the secondary current reflects an accurate relationship to that of the primary current. The most basic design of a CT consists of a length of wire wrapped many times around a silicon steel ring passed over the circuit being measured. The CT's primary circuit consists of a single turn of conductor, with a secondary consisting of many hundreds of turns. The primary winding may be a permanent part of the CT consisting of a heavy copper bar to carry current through the magnetic core. Window-type CTs are also very common. These CTs will have circuit cables run through the middle of an opening in the core to provide the single turn primary winding. The primary circuit is largely unaffected by the insertion of the CT. The secondary current rating is typically standardized at either 1 or 5 amps. Therefore, if a CT is rated at 4,000 to 5, the CT would provide an output current of 5 amps when the primary is passing 4,000 amps. A current transformer is designed to step down current to make instrumentation possible. Now, in the example CT shown, the CT is a 400 to 5 ratio. For every 400 amps of current pushed through the window of the CT, 5 secondary amps will flow. This is a ratio. So if 200 amps were flowing through the window of the CT, 2.5 amps would be flowing in the secondary circuit. The CT allows the current level to be lowered for instrumentation purposes. This allows relays, meters, or other instrumentation to sense a current at a level that is practical. Now, the load or burden in a CT metering circuit is the impedance presented to its secondary windings. This impedance will be largely resistive. Typical burden ratings for IEC standard CTs are 1.5 VA, 3, 5, 10, 15, 20, 30, 45, and 60 VA. ANSI IEEE burden ratings are B-.1, 0.2, 0.5, 1, 2, and B-4. Now, this means a CT with a burden rating of B-0.2 can tolerate up to 0.2 ohms of impedance in the metering circuit before its output current is no longer a fixed ratio of the primary current. Switch blocks, meters, and intermediate conductors will all contribute to the burden of a current measurement circuit. The conductor between the meter and the CT will typically be the source of excess burden. The CT will produce a voltage necessary to push the secondary current through the load. In this example, the secondary load, the meter, element, and wire, is 1 ohm. Therefore, the CT will build up 5 volts to push the 5 amps of current. Here's another example with the CT pushing the same amount of current into a 10 ohm load instead of a 1 ohm load. Here the CT will have to build up 50 volts in order to push the same amount of current. Since power is equal to volts times amps, here the CT must produce more power, 250 VA instead of the 25 VA shown before. Therefore, the CT must now work harder as the burden of the circuit increases. The CT can only produce so much voltage. It is limited by its physical construction and how much voltage it can produce before it saturates. Once the CT hits its limit, it will go into saturation. When we test CTs, one of the tests we perform is a saturation test. Typically, the larger the physical size of the CT, the higher the saturation will be. Once the CT reaches its saturation point, it will no longer accurately produce its current ratio. Now, the knee point of a CT is the magnitude of the secondary voltage after which the output current ceases to follow linearly to the input current. Or in other words, the one-to-one relationship between the input and output is no longer within declared accuracy. When testing, a voltage is applied across the secondary terminals and magnetizing current will increase in proportion to the applied voltage up until the knee point. Now, the knee point is defined as the point at which an increase of applied voltage of 10% results in an increase in magnetizing current of 50%. The knee point voltage is less applicable for metering CTs since their accuracy is generally much tighter and constrained within a very small bandwidth of the current transformer rating. The knee point, however, is very important to protection CTs since they are exposed to currents of 20 to 30 times rated current during a fault. Now, here is a typical saturation curve for a CT. Note that for the 400 to 5 CT, it saturates around 50 volts. This means that if the CT needs to produce voltage higher than 50 volts, it will not be able to use its ratio of primary to secondary current accurately. To test this CT, we would apply voltage to the secondary terminals of the CT. Now keep in mind, in a real circuit, the CT builds up a voltage to push the desired current. Now, as we apply voltage to the CT secondary terminals, the current drawn by the CT is the excitation current. As we hit the saturation point of the CT, we are no longer able to raise voltage on our test set without a large amount of current. This is how we know when the CT saturates. This curve generated from the test results must match the saturation curve published by the manufacturer of that CT. Now, we apply voltage on the secondary terminals and determine where it will saturate. In a real circuit, the CT builds up a voltage to push the desired current. These are the same points. Saturation tells us something about the voltage class of the CT. If it is a C100, it should not saturate until at least 100 volts. Shorted turns will greatly lower the saturation point. And the saturation point tells you how much current the CT can drive in a circuit if you know the burden. So, let's take a look at circuit burden. Again, if we push 5 amps and it takes 5 volts to push the 5 amps, the burden would be 25 VA. Now, this is the burden that is seen by the CT. So again, here we see, in order to drive the 5 amps, it needs to build 5 volts, or a power of 25 VA. Now, what if the load is an instrument relay and it is set at 100 amps? So, if 8,000 amps is flowing on the primary, 100 amps would need to flow on the secondary to maintain the proper CT ratio. To push 100 amps through the load, the CT must develop 100 volts. That's basic Ohm's law. So, is there any chance of this relay seeing 100 amps if the CT was the 400 to 5 CT shown earlier with a saturation point of 50 volts? It would never see the required amperage. All right, now let's look at principles of a differential protection scheme. The principle of a differential protection scheme is a simple conceptual technique. The differential relay compares the primary current and secondary current of power transformers. If there is an unbalance found between the primary and secondary currents, the relay will actuate and intertrip both the primary and secondary circuit breaker of the transformer. Suppose you have a transformer with a primary rating suppose you have a transformer with a primary rated current I sub P and secondary current I sub S. If you install a CT with a ratio of I sub P divided by 1 amp at the primary side, and similarly you install a CT with a ratio of I sub S divided by 1 amp at the secondary side of the transformer, and the secondary of both CTs are connected together in such a manner that the secondary currents of both CTs oppose each other, or in other words, the secondary of both CTs are connected to the same current coil of the differential relay in an opposite manner, The result would be no current in that coil under normal working conditions of the transformer. Now, if, however, any major fault occurs inside of the transformer and alters the normal ratio of the transformer, the secondary current of both transformers will no longer remain the same. Since the secondary currents at the CTs are no longer the same, a resultant current will flow through the current coil of the differential relay. This will actuate the relay and intertrip both the primary and secondary circuit breakers. Now, does the polarity of the CTs matter? Well, yes, they do. Also, to correct for phase shift of the current due to delta Y configuration of the transformer winding, the current transformer's secondary should be connected in delta and Y as shown here. Now, warning, never open circuit a CT. If the CT becomes open-circuited, it will try to develop enough potential to push the required secondary current, in this example 5 amps. With an open circuit, it can build up a very large potential and can cause serious injury. All right. Let's take a look at common field tests for CTs. So, what tests should be performed on a CT? Well, part of the answer depends on whether it is a routine maintenance test interval, a major maintenance test interval, or acceptance testing. During acceptance testing, all aspects and characteristics of the device are tested. You want to be certain to receive what you paid for, and that the device can be used at all settings. Maintenance testing is performed to ensure the device is suitable for continued service and is usually only done at the current taps or settings. For CTs, the most common field maintenance tests are the ratio test, saturation test, insulation resistance, and burden test. Acceptance testing on a CT usually involves performing the above listed tests on all ratios and taps, plus a polarity and a burden test. The NETA maintenance testing standards list the burden and polarity tests as maintenance tests as well. However, if the CTs have been tested in the past and properly documented, there isn't much chance that the polarity is going to change. The burden test is another story. Considering the problems an overburdened instrument transformer can cause, the burden test should always be considered during maintenance testing. Unfortunately, this important test is neglected even during acceptance testing. Now, when testing CTs or any other device, it is important that you understand the test set that you are using. Now, two commonly used test set brands are the Vanguard and the Megger test sets, as seen in this slide here. Now, if you are using the Vanguard test set, you will need to program the maximum voltage you wish to apply to the CT secondary and maximum current that you wish to measure. The Vanguard tests can be operated either manually or using their remote software. Let's just take a quick demonstration of how the remote software would work.
Remote operation of the Vanguard EZCT 2000. Step 1. Go to Application Setup. Make sure you are set to the correct COM port. Step 2. Create a test plan. Enter customer job information. Select the EZCT test set that you intend to use. Select the taps and tests you wish to perform. Select the maximum test voltage that you want applied. In this example, we will use 50 volts for a C20 CT. The current limit is typically set to stop the test at 2.0 amps, but this will depend on where the CT saturates. When complete, save your test plan. Step 3. Run your test plan.
Okay. Now, if we look at the manufacturer's saturation curve for this 400 to 5 CT, we would see that 2 amps is way past the need curve. This current setting would give us very good results and would clearly show the need point of the CT. Also, based on this saturation curve, the test voltage setting for this CT could be set as low as 100 volts, since the curve shows saturation around 50 volts. Now, why is it important to know your test set and expected saturation of the CT you're testing? Well, here is an example of a test report that was turned in by a technician who was using the Vanguard EZCT test set. The technician had similar results on all of the 50 to 5 CTs that he was testing that day. Where is the need point on this curve? What would you do if this was your test results? And do you believe that this CT and all the 50 to 5 CTs that you were testing on this particular day were bad? Was the test set maybe not operating properly? How would you go about troubleshooting to find the answers? Well, let's answer these questions. We can see that the test set did ramp up to the 2 amp maximum current, and then it stopped. So it does appear that the test set did what was asked of it and tested to the 2 amp limit that was set. Now, one of the first things that should have been done was to determine the type of CT that was being tested, and then to find the manufacturer's published saturation curve. Now, in this example, the CT that was tested was a Model 594 manufactured by Instrument Transformers, Inc. Note that the current at 2 amps is very similar to what the captured test results had shown. For this CT, however, the knee of the curve is up around 5 amps. Therefore, when the test was run, the test set stopped at 2 amps and not enough data was captured. This is somewhat common to lower ratio CTs like the 50:5. It is important to understand what you are looking for when you test and always go to the manufacturer's curve when you're in doubt. All right, let's watch another demonstration, setting the current limits on the EZCT via the front panel.
A current limit of 0.2 amps is selected. As a result, not enough data is collected to show the knee point. Let's get the manufacturer's data for a FlexCore 143-500 50-5 CT. Let's try again. Based on the manufacturer literature, 2 amps should be fine.
Okay, let's move on. Now, as I mentioned, another popular test set is the Megger Relay CT test set, or MRCT. So, let's take a demonstration of this test set.
With the Megger Relay CT test set. Select Setup. A maximum test voltage can be set. Testing will end when the max is reached or when saturation occurs. Review other setup options. Select Report to enter nameplate or customer information. Select Run All Tests. Voltage will ramp until max limit is reached or until saturation is reached. The current limit is fixed at 1 ampere in auto mode.
Notice how this test set has a demag function and will demagnetize the core of the CT after performing the saturation test. Upon completion of the saturation test, the unit will automatically go into the ratio test, since that was one of the tests that was selected in the setup.
The MRCT will automatically complete a PowerDB test sheet.
PowerDB is a very popular databasing reporting software that many of the test companies utilize. And that was a brief demonstration of the Megger relay CT test set. All right, let's move on. Let's enter the world of potential transformers. Now, a potential transformer, also known as a voltage transformer, is also a type of an instrument transformer. It is a step-down voltage transformer that reduces the high-level voltage to a safe low level. The output voltage of the potential transformer can be measured by connecting an ordinary voltmeter. Furthermore, it also provides isolation between the high voltage power circuit and the low voltage measuring circuit. The working of PTs is like any conventional transformer. The electrical energy is transferred between the primary and secondary winding through magnetic induction. The alternating voltage at the primary generates alternating magnetic flux in the transformer core. Since both windings use the same core, this alternating flux induces a voltage in the secondary winding. Thus, current starts to flow in the secondary winding. Since the primary has a greater number of turns compared to fewer secondary turns, the voltage induced in the secondary is very low. The secondary voltage is measured by using a standard voltmeter. Using the turns ratio equation of the transformer, we can calculate the primary voltage. That is to say, the primary voltage divided by the secondary voltage is equal to the number of primary turns divided by the number of secondary turns. Now, the potential transformer is connected in parallel with the circuit, as opposed to the CT that is connected in series. The primary of the PT is directly connected to the power line whose voltage is being measured, while the secondary is connected to the voltage measuring instrument like a voltmeter, wattmeter, etc. Since the voltage in the secondary is very low, an ordinary voltmeter can be used to measure it. Now, the primary and secondary of the PTs are magnetically coupled through mutual induction, where the primary voltage is reduced based on the turns ratio of the transformer. The primary voltage can be up to several thousand volts, while the secondary voltage falls below 110 volts. Both windings are electrically isolated, but for safety reasons, the secondary winding is grounded at its one end. The potential transformer, or PT, can be classified into two types based on its function. Let's look at metering potential transformers. The metering type PTs are instrument transformers used for the measurement of voltage. They are low rating transformers with high accuracy. And then there's the protection potential transformer. Such type of PT is used for providing protection because their windings are electrically isolated and the low voltage side is not directly connected to the high voltage side. The potential transformer can be classified into types also based on its construction. We have the electromagnetic potential transformer. The potential transformer that uses electromagnetic induction to transform high voltage into low voltage is obviously called the electromagnetic PT. There are conventional wound type transformers having primary and secondary windings wound around a magnetic core. Therefore, they are also called wound-type potential transformers, having shell type and core type. Such PTs do not use any other electronic component to reduce the voltage, such as a capacitor. The drawback of electromagnetic PTs is its insulation problem at high voltages, due to which its design becomes very complex for voltages above 10 kV. Therefore, capacitive dividers are used in the following type to eliminate the insulation problem. And that introduces us into the capacitive potential transformer. The capacitive potential transformer is the combination of capacitive potential divider and electromagnetic transformer or auxiliary transformer. The capacitive potential divider is used to divide the high line voltage to reduce it below 10 kV. The capacitors are connected in series at the primary side of the auxiliary transformer. The auxiliary transformer further reduces the voltage with high accuracy to be measured by the voltmeter. These transformers are used for power lines. All right, now let's talk about errors in PTs. In an ideal transformer, the primary and secondary voltages are in exact proportion as its turn ratio, and they are both in phase. But practically, there is a voltage drop at primary due to its reactance, which creates voltage ratio error and phase shift error. Here are some of the errors that may occur in a PT. The ratio error. The ratio error is the change in the voltage ratio due to the variation in load. Varying load changes the magnetizing current and the core losses that affect the secondary voltage of the PT. In simple words, the normal ratio differs from its actual ratio. Ratio error is given by the following equations, where the K sub n is the normal ratio or the rated ratio, R is the actual primary to secondary voltage ratio. The nominal ratio is the ratio of rated primary voltage to rated secondary voltage. Okay, another error is the voltage ratio error. The voltage ratio error is the difference between the ideal voltage and the practical or actual voltage. And here is the formula to find the voltage ratio error, where the K sub n is the nominal ratio, the rated ratio, V sub P is the actual primary voltage, and V sub S is the actual secondary voltage. Phase angle error. The phase angle error is the difference between the phase of primary voltage and the reversed secondary voltage. Ideally, the primary voltage is in phase with the secondary voltage in reverse. But practically, there is the reactance of the windings that shift the phase of the secondary voltage, creating phase angle error. Now, the effects of burden on the performance of a potential transformer are as follows. If we increase the burden, the secondary as well as primary current will increase, but the primary voltage will remain constant because primary of the PT is connected to the line. The secondary voltage will decrease. Therefore, the voltage ratio will increase. Thus, we see that increasing the burden increases the error in the ratio. Also, as the power factor of the burden reduces, the transformation ratio of potential transformer increases. All right, here are some applications of potential transformers. They are mainly used for measuring high voltages. They are used for electrical protection purposes. They are used in metering devices for energy billing. It is used for monitoring industrial load. They are used in power line carrier communication networks. They are used for synchronizing the generator and feeder. Now, testing of a PT. First, perform insulation resistance tests, winding to winding and each winding to ground. Also, you want to test polarity and to perform a turns ratio test. And that concludes our webinar today on current and potential transformers. As I state every month, thank you so much for your participation and attending our webinars. Again, Matt and I love doing these webinars every month. We love seeing all the familiar names pop up on our registration. And we do truly hope that you are getting benefit out of these webinars. All right, without further ado, let's get to those questions.